Okay, so welcome back, everyone. Before we continue on to our next talk, we wanted to mention the GFGD donations. We've currently raised over £100, so thank you to those who have donated. And if you do want to donate, kindly, the link will be in the Zoom chat as well as the barcode scanner on some backgrounds. Our final talk of the day is given by Professor Sonia Tikoo from Stanford University, California. Her talk is on magnetic fields in the solar system. This will be a recording that Sonia has made for us. Sonia is currently in the audience and will be available to answer any questions straight after her talk. She also has a Discord chat, just like the rest of our speakers.
Hello, everyone. And first of all, thank you so much for the invitation to speak here at the Herdman Symposium at Liverpool. It is such a great honor to be part of this event. And today I am really excited to take you on a tour of magnetic fields in the inner solar system. Core dynamo magnetic fields are produced by organized motion of conductive fluid inside planetary bodies. And most of the time, this conductive fluid is sourced from the liquid metallic core of a planetary body. And so if you can either through paleomagnetism or crustal magnetism demonstrate that a planetary body currently generates or once generated a magnetic field, that can tell us a couple things about the planet. First of all, if there is a core dynamo, it tells us that the planet has undergone differentiation and segregation into a metallic core and an overlying silicate mantle early in its formation process. Then the second thing that a dynamo can tell us about is that there's some mechanism to sustain advection inside the planet's interior. So there are a few different ways that you can have such organized fluid motion. The canonical way to generate a dynamo is through convection. Basically, hot metal rises, cold metal falls, and it is through thermal convection that you can generate a long-lived magnetic field. And that mechanism can tell us something about the long-term thermal evolution and secular cooling of a planetary body. In addition to thermal convection, chemical buoyancy derived from inner core growth can provide an additional mechanism that can bolster a dynamo and also release latent heat as an inner core starts to crystallize. Then finally, it's possible that there are non-traditional dynamo mechanisms that can operate, such as mechanical stirring of a fluid core. And this type of mechanical stirring can result if a core is perturbed by some kind of external force. And we'll learn a little bit about that later in today's talk. So if we take a quick walk, a jaunt around our solar system and look at where dynamos are or used to be present, we can learn a lot about different planets. So currently, right now, we are sitting on Earth in about a 50 microtesla magnetic field. Basically, our field has a largely dipolar structure. There's sort of a northern lobe and a southern lobe. About 90% of our field is dipolar at the surface. Then if we go a little smaller in planetary size, we can look at the planet Mars. Mars doesn't have a dynamo anymore. Its magnetic field went extinct sometime, around or a little younger than 3.7 billion years ago, we think. But there is a memory of the ancient Martian field preserved in Mars's crust as a crustal remnant magnetization that is detectable by spacecraft. Going a little smaller, we can visit the planet Mercury. Mercury currently also has an active dipolar magnetic field, but it's much weaker than Earth's. It's about 200 or a few hundred nanotesla in intensity at the surface. Then finally, we've had paleomagnetic studies in the last decade or so that have looked at meteorites, and we have learned that meteorites record remnant magnetization in them that may be from ancient dynamos that were only active for the first few million or 10 million years of solar system history. Now, you might have noticed that I skipped a couple bodies. One, I didn't talk about Venus. Well, Venus actually has no current dynamo field. But we don't know about its history in the past. We haven't sent spacecraft specifically with magnetometers to study the ancient history of Venus. It's possible that it never had a dynamo, or it's possible that maybe it did, and there is some crustal remnants in Venus, but we just don't know right now. And the second body I skipped, which is the body that I specialize in the most actually, is the moon. And the moon is actually a really interesting target for magnetic studies because it falls kind of intermediate between a planet-sized body, which can have an active dynamo, as we see for Mercury today, and asteroids, which are smaller and are not expected to have long-lived dynamos because they would have cooled off too quickly to sustain one for a long time. So later in the talk, we're going to learn a lot about the moon. But before I talk about the moon, I just want to go over how we study planetary magnetism. And as I kind of alluded to earlier, there's two ways to do this. The first way is to make spacecraft measurements of magnetic fields at other planets. And so in this case, we're either measuring the field from an active dynamo or whatever remnant crustal magnetism may be left over on a body after a dynamo ceases. The second way that we study planetary magnetism is by conducting paleomagnetic experiments on samples in the lab, and we try to measure the magnetization that is preserved in individual rocks. So before I talk about paleomag, I'm going to go over a little bit about what we have learned from spacecraft measurements of other worlds. I'm going to begin with Mercury simply because it's the closest one to the sun. And as I mentioned earlier, Mercury has a largely dipolar magnetic field, and it is actually a beautiful axial dipole where the dipole magnet axis lines up with the spin axis of the planet very nicely. On the Earth, there is a slight offset between the two. But one thing that's weird about Mercury is that its dipole is actually shifted northward relative to the center of the planet by about 20% of the planet's radius. And we don't actually know why this offset happens. And another weird feature about Mercury's magnetic field is that it is about 100 times weaker than the Earth's magnetic field. And that is a mystery. And the reason it's a mystery is because the size of Mercury's core relative to the overall planetary radius is much larger than that of the Earth. On the Earth, our core is about half of our planet's total radius. And on Mercury, it's something like 70 to 80% of the planetary radius. And so the reason that a larger core to overall radius ratio should produce a stronger magnetic field is because people have developed scaling laws for the intensity of terrestrial planetary dynamo fields. And one of the biggest things that can amplify a field strength is the ratio of the core radius to the overall radius. That field strength should be a function of that to the third power. So this should be a very large determinant in bolstering the strength of a field, but we don't see that in Mercury. And so the origin of why Mercury's field is so weak remains a great mystery in planetary science. And I'm not going to talk about that too much today because that's not my specialty, but there's a whole host of hypotheses behind that. But one thing that we do know about Mercury is that in addition to having an active dynamo, it also records remnant crustal magnetization. And due to the orbit of the spacecraft that measured Mercury's magnetic field called MESSENGER, it only came near the planet, very close to the planet, close to the North Pole of the planet. So because of that, we only have good crustal field measurements from about 30 degrees north and above. But based on those measurements, we can see that there are a lot of magnetic anomalies, or basically localized, very strong magnetic fields preserved in the crust on Mercury. And these are predominantly associated with impact craters, ejecta, and melt sheets, and maybe some magmatic features as well. But regardless, there are magnetic anomalies in the Mercurian crust that date to about 3.9 billion years ago. So this tells us that Mercury's magnetic field has probably been active for its entire history. I mean, we can't say what happened between then and now, but you know, it might have been active the whole time. So another thing people do is they try to take individual magnetic anomalies on Mercury and use inversion techniques to ascertain the direction of magnetization preserved at each of these anomalies. And they try to determine a paleopole for basically where the pole of the ancient magnetic field should have been for each of these isolated anomalies. And interestingly, what we find is that if we look at the southern hemisphere of Mercury, the ancient paleopoles are scattered, actually. They're not located at the planetary spin axis. So is it possible that Mercury's magnetic field was not always a perfect geocentric axial dipole? Or is it possible that there's something not quite perfect about these inversions? We don't really know, but it's possible that this is an indication of a different dynamo behavior in early Mercury history compared to what we see now. Now, let's move on to a different planet. Let's go to Mars. So Mars has had its magnetism measured by a couple different spacecraft, like Mars Global Surveyor and MAVEN. And what we find is that much of Mars's crust is also magnetized, particularly in the southern hemisphere. One thing that's interesting about Mars is a lot of its big impact basins, such as Hellas Basin here, are not magnetized, and neither is the Tharsis volcanic province, which you may have heard of because of its relationship to the Olympus Mons volcano, which is the tallest mountain in the solar system. And that tells us that maybe the Martian dynamo was inactive at the time that those particular features formed. But regardless, the earliest Martian crust definitely records ancient magnetization from a dynamo. And there are even some volcanic units on Mars that may record magnetization at about 3.7 billion years ago. So there appears to have been activity on Mars in the past for some amount of time. All right. So that's kind of what we've learned from spacecraft, from Mercury and Mars. I'll talk about the moon later. But before I get to moon's crustal magnetism, I want to talk about some of the research that we're doing in actual sample paleomagnetism to unravel the histories of fields on other bodies. So what we do is we study little pieces of rocks and we try to figure out the intensity and direction of ancient magnetization that is preserved. So before I get into that, I need to talk first about how rocks actually acquire magnetization in the first place. So it turns out that if you have an igneous rock, a lava, that has erupted on the surface of a planetary body, it starts out really hot. And then as it cools down, little magnetic minerals begin to form. On Earth, we think of magnetite, but sometimes on other planetary bodies in a reducing environment, we might just have metallic iron. So basically, a rock is going to form these magnetic minerals, but whenever it's very hot, these magnetic minerals are paramagnetic. They cannot hold on to any permanent magnetization. It is only when they cool down below the Curie temperature of the magnetic minerals that they can lock in magnetization. So if we have an ambient field that's present and it's biased in a certain direction, as the rock cools below the Curie temperature, the rock will record a magnetization in the direction of the ambient magnetic field. If a field is somewhat weaker, what ends up happening is that this magnetization acquisition process becomes less efficient. So you have a weaker net magnetization preserved. And finally, if there's no field present when a rock forms, the magnetization in a rock is random and becomes zero. So essentially, the way paleomagnetism works is when rocks form, their magnetization is oriented towards the ancient field direction, and the strength of the magnetization is directly proportional to the strength of the ancient paleo field. So on Earth, where we have developed all of our paleomagnetic techniques, we are really interested in understanding the history of our planet's dynamo. And so what we can do on Earth is we can go into the field, we can drill rock samples, and we can bring them back to the lab. And we get to deal with these nice samples that are like 1 inch across and they're easy to handle. And based on those individual samples, we can bring them to our paleomagnetism labs and we can begin to demagnetize them to unravel the original magnetization in a rock. And so how does that work? Basically, we consider magnetization to be a vector. It has an intensity and a direction. So let's just say that we're looking at 2 dimensions, north and east, and the original magnetization in a rock is called the natural remnant magnetization, or the NRM. A rock is an assemblage of individual magnetic minerals, some of which are hard to remagnetize. These are the big red grains in my plot. And some of these minerals are really puny and weak and easy to remagnetize, and they are susceptible to being contaminated. And those are the blue tiny grains here on my cartoon. So basically what we do in the lab is we start with what's in the rock naturally, the natural remnant magnetization, and we begin to remove magnetization using either alternating fields to randomize magnetization, or we heat it in an oven stepwise until all magnetization is removed. So here, let me partially demagnetize my sample with an alternating field of 2 millitesla. When I apply this field step, the weakest grains in the sample are randomized and they cancel each other out, but the rest of the remnant still remains. Let me demag it some more. 5 millitesla, 10 millitesla, boom. Now I have completely randomized this vector of contaminating magnetization and it's gone. I'm going to keep demagnetizing my sample now. I'm going to walk it to the origin. And wow, whenever I have a linear vector that trends to the origin, that is the original magnetization that was recorded in a sample at the time that it formed. So whenever we want to understand the history of a planetary dynamo, we want this origin trending vector. Now, once we have that origin trending vector, we want to know what field strength does that vector correspond to on an ancient planetary body. And so what we want to do is we want to figure out what the paleointensity recorded by that rock is. And the way we do this is we stepwise demagnetize a sample. In this case, I'm going to describe a thermal demagnetization experiment. So I'm going to start out with my original natural remnant magnetization, and I'm going to demagnetize it to increasing temperatures. And so here are increasing temperature steps, and here's the intensity of the NRM remaining at 525 degrees Celsius, down to 585 degrees Celsius, at which point is the Curie temperature of magnetite and you don't have magnetization anymore. So what we end up doing is we stepwise heat the sample and see how much the NRM decays. Then we also start out with our sample after it's been demagnetized to each temperature, and we actually apply a laboratory field with a known value. We call this B lab. And we apply the known laboratory field at an increasing temperature as well to impart magnetization to the sample. So in the end, what we get is we have a trend of natural remnant magnetization remaining at each temperature step. And we also have a plot of the partial thermal remnant magnetization that we have imparted into the sample in the lab, again, at the same temperature steps. And basically, we calculate paleointensity by this formula. The strength of the ancient field is the strength of the ancient magnetization divided by the laboratory magnetization that we measure and observe, multiplied by the strength of the known laboratory field. So essentially, the slope of NRM remaining versus partial TRM gained gives us the paleointensity of a sample. And this is the basis for all of these paleomag studies that we are doing. And whenever we do that on Earth rocks, we can develop a history of the Earth's dynamo-magnetic field. Now, I'm not talking about paleointensity here. What we do is we convert paleointensity values to something called the dipole moment of the Earth. And so what that means is basically how strong is the bar magnet of the Earth if we were to basically consider each paleointensity value and convert it to a magnetization strength of a magnet that is centered at the center of our planet. And if we look at the Earth data, which are these gray circles here, we can see that we actually have paleointensity results for the last 3.5 billion years. We can learn a lot about the history of Earth's magnetic field by studying rocks of different ages. And so we have this paleointensity record, which are the gray circles and the associated errors. But what does that tell us beyond just the strength of the field and the fact that it was present? Well, it can tell us something about the interior evolution of our Earth and the cooling of our Earth. So there are people like Peter Driscoll here, who I'm citing, who can basically construct thermal evolution models of the Earth's interior and see how the core cooled and how the core mantle boundary cooled and how the Earth's mantle may have cooled, and try to predict essentially when the core would have cooled enough to actually start crystallizing. And whenever the core started to crystallize and you have formation of the inner core and you have this additional energy source for the dynamo, you may see an uptick in paleointensities. So there is some kind of effort to link changes in paleointensity behavior with the onset of core crystallization processes. Now, the exact age at which this happened is a bit uncertain, but from the paleointensity records, estimates range between like 1.3 billion years ago to about 500 million years ago. But the point is, this is an active field of research with the overall goal of understanding the interior evolution of our planet. And this is actually the same motivation that we use to study the history of the ancient moon's magnetic field. Spoiler alert, it had one. So the moon generated an ancient field. But what I want to learn about is how strong was it? How long did it last? And what powered it? What can we learn about the thermal evolution of the moon? So first, I'm going to start by talking about the historical development of the field of lunar paleomagnetism. Then I'm going to talk about the current state of what we know. And I'm going to close by talking about avenues for future exploration. So beginning with the Apollo missions, the astronauts actually took magnetometers to the lunar surface, and they measured crustal field strengths of 3 to 300 nanotesla. This is way weaker than the current terrestrial field that we have here on Earth, but it indicates that there was some remnant magnetization present on the moon, even if there was no current lunar dynamo. So another thing the astronauts did was they brought back a bunch of samples to the Earth. So paleomagnetists like me, but the earlier generation, could measure them and actually do paleointensity studies of lunar rocks. So what we're looking at here is a plot of paleointensity for different rock samples. And you can see the different samples and their lithologies in different colors versus time, or the ages that the samples formed. And what you can see is that we have a few different eras in lunar history. We have an early period where there are high paleointensities, even up to 100 microtesla, which is double the kind of the strength of the Earth's field today. But there's a lot of scatter as well. So we're not quite sure what's going on here. Then there's a gap in sample ages because they just didn't pick up any rocks with intermediate ages. And then there's some like maybe some weak field records later on, but we don't know if those points are real or not back then. There was still a lot to be learned. A thing that compounded these mysteries about the lunar dynamo was there was this hypothesis that giant impact events can actually produce magnetic fields. Basically, what would happen is you would have a giant impact and it would create a plasma that would wrap its way around the moon from the location of an impact. And basically, the plasma would trap the solar system magnetic field and amplify it at the antipode of the moon, and rocks on the other side of the moon from the crater would get magnetized by this process. So what we have here is we have some major impact basins on the moon. On the near side, there's Imbrium Basin, Serenitatis, and Crisium. And it turns out that if you look at the antipodes of these three craters, there are actually strong crustal magnetic anomalies at these antipodes. And on top of that, there's another crater here, the biggest crater on the moon, called South Pole Aitken Basin. And incidentally, all of these anomalies are coincidentally also located near South Pole Aitken Basin. So at the end of the Apollo era, there was still this mystery about whether the magnetization on the moon had anything to do with the dynamo at all, or whether these were all impact processes. So that's something we had to reconcile. Another thing we had to reconcile was whether the magnetic records obtained during the Apollo era were actually from the moon. After all, we brought these rocks back in a spacecraft, and the rocks were not magnetically shielded. They may have been handled with tools that were also non-magnetic. Whenever they processed the samples at Johnson Space Center, they cut them dry many times using a bandsaw, and the friction from that heating may have imparted a partial thermal magnetization. And then finally, rocks can acquire some overprint magnetizations from long-term exposure to the weak Earth's magnetic field. So in order to do lunar paleomagnetism properly, we have to exclude all of these possible effects. So what's the current state of what we're doing? Well, it turns out that, in the last few years, people have been investigating the impact fields hypothesis. And what we have found from modeling is that it turns out that the field strengths generated by, plasmas moving around the moon and squishing the, solar magnetic field or the solar system magnetic field, that amplification process is actually not strong at all. The strongest fields that are produced by the impact plasmas process at the antipodes are something like less than 100 nanotesla, which is not nearly strong enough to reproduce the microtesla, several tens of microtesla, 100 microtesla fields that we infer from the lunar paleomagnetic record. So the takeaway is that impact fields are too weak. Lunar crustal magnetism must be from a dynamo. Then we also implemented some modern revisions to protocols to account for some of the Earth contamination possibilities. We conduct high resolution, high field alternating field demagnetization to remove any magnetic overprints that exist in samples. We research the cutting history of all the rocks that we study, and we screen them to make sure they have not been bandsawed or gotten hot from that process. So we really look at this carefully. And then finally, we conduct experiments that test how much contamination could be from long-term exposure to the Earth's field, and we exclude samples that have experienced that or are susceptible to that. And then another thing that we do is we actually constrain rocks' shock and thermal histories, because it turns out that shock and heating from shock can actually also reset magnetization. So we do a lot of shock barometry by looking at textures in individual samples in thin section to make sure that they are not messed up. And we also do argon-argon thermochronometry, which tells us about the heating history of the rock. And basically we can tell if a rock has experienced any other heating other than just the normal diurnal day-night cycling as they are heated by the sun at the lunar surface over a long period of time, which is only to about 100 degrees. So, which is much less than the 780-degree Curie temperature of iron. So we do all of these things to screen samples. And then finally, another thing that we do is we measure multiple pieces of the same rock that are all mutually oriented with respect to each other. And we want to make sure their magnetizations have the same direction and that they're uniform. So here's one example. I studied Apollo sample 15498. I got 5 different parent chips from this rock from different places in the rock. And I demagnetized 12 pieces, and they all had more or less the same magnetic direction. So we would say this is a robust identification of an ancient dynamo field. Another advance we've had recently is we can do controlled atmosphere heating of lunar rocks. Why does this matter? Whenever we heat Earth rocks that formed in our Earth's oxidizing atmosphere, we don't have that much thermochemical alteration. We do have some, but it's not nearly as bad as if we heated a moon rock in air, because moon rocks formed in a reducing environment. And if we heated them in our atmosphere, they would just oxidize and it would totally mess up our experiments. So now we have new ovens that can use hydrogen and carbon dioxide mixtures to replicate the oxygen fugacities on the moon. And we can successfully do thermal studies of lunar rocks to chip away at their magnetization using that method. And so it turns out that we were able to start doing thermal paleointensity studies of lunar rocks. So again, I'm going to talk about Apollo sample 15498. I started out with this sample. I measured its natural remnant magnetization. I heated it stepwise to increasing temperatures to reveal the original magnetization vector, which is shown in green here. And basically, I was able to find that origin trending vector. And I was able to do a paleointensity study, again, comparing the NRM lost to the partial TRM gained in the laboratory. And using the slope of this origin trending vector, I was able to calculate that this rock recorded a 5 microtesla magnetic field on the moon. So using methods like this, we have begun to assemble a modern paleointensity timeline for the moon. And from modern studies, we actually find results that are not too dissimilar from the Apollo era. We have evidence for strong ancient magnetic fields early on in lunar history. However, there is still some variability. There are some rocks we don't have conclusive results for, but we can place upper limits on what the strength of the field had to be weaker than, because if it was stronger than that, we would have seen something in the rocks. Some rocks are not great magnetic recorders, so we have to only resort to upper limits for those. Then we have a couple young samples that have a magnetic field record, like 15498 here at about 1.5 billion years ago. And then there's some other samples that have been recently studied that are less than 1 billion years old, and they have no magnetic field record at all, and they are fantastic recorders, which means that the field around whenever they formed was less than 100 nanotesla. So that tells us that the lunar dynamo probably died by about 1 billion years ago. So we can construct this chronology from the modern data set. And so we have this timeline. There's the early field, there's a high field epoch, there's a decline, there's maybe an intermittent or weak field, and then it ceased. Now, it turns out that this high field epoch, though, is still a conundrum because it's really hard to generate strong magnetic fields with the small lunar core, which is less than 400 kilometers radius and an overall 1700 kilometer radius body. It turns out that to generate a 50 microtesla field for 300 million years during the high field epoch, you require 12 times the possible radioactive heat budget of the core for the moon. It's essentially impossible to have a continuously operating dynamo that long. So this means that convection unaided cannot readily explain the early high field epoch on the moon. But this has led to the hypothesis that maybe some other mechanisms were operating on the moon. Is it possible that instead of a core dynamo, the moon had a basal magma ocean dynamo, and maybe this basal magma ocean was conductive enough to actually generate a field? And because it's closer to the surface than the core, it would have been amplified in intensity. That's one hypothesis. Another interesting hypothesis is that mechanical effects such as mantle precession or precession between the outer core and the inner core could have also generated a magnetic field. So these are other factors that are being considered, and it's really cool to see the moon as an avenue to explore non-traditional dynamo mechanisms. So a lot of work is going into this now, and maybe we can, converge on a solution once more modeling studies are done and refined more. But it's possible that maybe the high field epoch was not always so high field. There are even modern studies, and this is a paper written by Cecile Cornette in 2012, that looked at rocks that should have formed during the high field epoch between 3.5 and 4 billion years ago. And, in theory, you would think they would record strong fields based on what we see in the other samples, but their remnants actually looks like noise. There's some overprint on it, but whenever you get to higher alternating fields, there's no origin trending vector. It looks like spaghetti. So it's possible that samples like this, and there's a bunch of them, indicate that the field was not always so strong during the high field epoch. And if that was the case, it's actually a lot easier to explain the lunar dynamo using intermittently enhanced convection versus a continuous, strong core convection. And so this is another possibility that maybe this lunar dynamo is not as confounding as we originally thought. So what we're doing here in this plot is we're going to combine the modern studies, which are outlined in red, with the Apollo era studies that are outlined in black. And what we see again is that you have a period of variability earlier on, a decline, a weak field, possibly intermittent dynamo, and cessation of the dynamo near the end of its history. But what can we do with this now? Is there any way we can extract information about what the lunar field might have actually been doing? I've actually had my grad student, Jian Zheng. She has been going through some of the Apollo era data and filtering it for quality to see if we can extract some data points that live up to our modern standards for how we consider our data and whether there might have been a dynamo or not. And we're actually filtering and we're trying to combine our data sets and understand the history of variability of the lunar dynamo during that high field epoch between 3.5 and about 4 billion years ago. And what we find is that if we look at all of the data from the Apollo era and modern studies, there's a lot of variability, but if we clean it up, there's still a lot of variability in the intensity of the dynamo. So here we're looking at the virtual axial dipole moment for the moon, and we find that there is about an order of magnitude or perhaps a little more variability in the intensity of the lunar dynamo field, which is exactly comparable to about a factor 15 variation in the intensity of the Earth's magnetic field over a similar period of time of about 300, 400 million years. So we might actually be seeing changes in the lunar field intensity due to factors like magnetic reversals or secular variation of the lunar field. And so it's an exciting time as we dig into this problem some more, and lunar paleomagnetism becomes more like Earth paleomagnetism, and we try to start to geek out on these problems. Now, finally, I want to close with some of our avenues for future exploration. What we want to do now is we want to fill in the paleointensity record better. And that means we need to analyze more samples. We're starting to run low on Apollo material that's accessible to us, but luckily NASA is planning to send the Artemis missions to the moon, to send the first woman and the next man to the moon in a few years. And hopefully we can get more rocks then. Another avenue is to have additional robotic or crewed exploration that continues to sample rocks, or at least if you can't sample rocks, make crustal magnetic field measurements at the surface to see how the intensity of the field changes over long distances. And so this is a proposed traverse for a mission concept called Intrepid, which could travel, over 1,000 kilometers on the moon and make magnetic field measurements, which would be so much fun and so useful to have. Another future objective that we need to work on is constraining the geometry of the lunar dynamo field. As with Mercury, people have tried to fit paleopole directions to individual magnetic anomalies, but also like Mercury, the paleopole directions are all over the place. So the question is, was the lunar dynamo actually not an axial dipole, or is there something going on with these inversions? We don't quite know why there's so much scatter right now, but that's future work. All right, so in the end, I just want to talk about solar system dynamos again. Mercury had an early dynamo for sure. It has a dynamo today. It might have had a dynamo the whole time. The moon had a dynamo early in its history that probably ceased by 1 billion years ago. Earth definitely has had a dynamo for almost all of its history, up to 3.5 billion years ago. And there are ongoing paleomagnetic studies looking at the early Archean and also perhaps the Hadean to try to understand whether the dynamo could be earlier than that on the Earth. Mars appears to have had a dynamo in its history, perhaps intermittently prior to 3.7 billion years ago. And we have some paleomagnetic studies from some meteorites that are from parent bodies that underwent differentiation and formed a dynamo as well. So the asteroid Vesta appears to have generated a dynamo. Parent bodies of the Angrites, Palasites, CV chondrites, and some iron meteorites also appear to contain dynamo records. So the takeaway here is that magnetic field generation is actually a very common thing in differentiated planetary bodies. And so the more we keep looking for it, the more we are going to learn about the histories of what's going on in the interiors and the heat loss of these planets as they evolve. And then the second conclusion set that I have is about the moon. So paleomag and crustal mag show the moon definitely, or at least according to what we can tell, had a dynamo. The early dynamo may have at times rivaled the modern Earth's field, but it's possible that the average field, even during the high field epoch, was weaker and that there were just substantial field variations. Dynamos driven by core convection or core crystallization can explain weak fields, but stronger fields may require non-traditional mechanisms, such as a basal magma ocean dynamo or a precession dynamo. But all in the end, additional studies will help fill in these temporal gaps, help us determine field geometries, and help us distinguish between the different dynamo mechanisms that have been proposed. Lunar magnetism is a mystery, and it's going to keep us busy for a long time, but I'm really looking forward to continuing to work on it. Thank you so much again for the invitation, and I'm happy to take questions.
Okay, so thank you, Sonia, for such an interesting talk. It was really out of this world. It was great to have you join us, and we also have some time for questions from the Discord chat. So our first question says, hi, thank you for the really interesting talk. There are some studies about the discrepancies between using thermal and microwave methods to determine paleointensity. Have you considered using microwave methods to determine paleomagnetism of the lunar rock samples? And do you think there will be any differences in paleointensity values?
Yeah, that's a great question. Actually, we haven't done this with the modern studies yet in the last 10 years, but there were some microwave studies done during the Apollo era, and sometimes the results were similar, sometimes they were different, but that's definitely something we should look into more. We also need to investigate more whether microwave heating could still induce oxidation, even if it's rapid compared to heating in an oven. So just yeah, but that's something that we could look into more for sure.
Another question we have is, could the methods you're applying to the Earth's moon be applied to moons on other planets?
Let's see. So it can definitely be applied to rocky bodies. Mercury doesn't have a moon, Venus doesn't have a moon, Mars has Phobos and Deimos, which could be interesting to study paleomagnetically if we ever got samples back from there. But those bodies are very small, and probably don't have a core, because they're sort of like rubble pile asteroid type things, in terms of their densities. So we're not really expecting to see a magnetic field generated by Mars's moons. Then whenever you get to the outer solar system, a lot of the moons that we have out there are what are known as icy satellites. So they're basically covered in ices, a lot of the time, and that might be difficult to do paleomag on because we can't actually get to rocks. But and then there's Io, which is a rocky moon, orbiting around Jupiter, but it's such a volcanic world that's continuously erupting that I think the whole body's probably above the Curie temperature. But yeah, so, but I mean, generally we can do this on rocky materials, and a lot of our focus has been on meteorites for that reason.
Okay, we've got another one in the Discord that says that they wanted to ask whether you think the lunar paleomagnetic age differences in the pre-existing studies could be influenced by the type of rock surveyed, as between 3.5 to 4 GA, the predominant rock type was basalt, as opposed to around 2 GA to the present day, the main rock type was breccia, which is predominantly sedimentary.
I'm gonna read the Discord question again one more time on the server just to make sure that I'm getting this right. Um, okay, yeah, so it's possible that for some of the room temperature paleointensity methods that we use, I didn't get into the differences, but we do thermal paleointensity experiments on some rocks and room temperature experiments on other rocks. We are able to do thermal experiments, which should be more accurate on breccias and impact melt rocks, because they contain minerals that are more favorable to those experiments. The basalts are harder to do thermal experiments on because they alter more easily in a heating experiment. So there is more uncertainty associated with the paleointensities we get from basalts because of the complexities with the paleointensity methods that we are using. But we think that the results from the breccias should be more accurate. But I will clarify that the breccias that we measure on the moon are not sedimentary. They're produced by impact processes. So in all of these cases, you have an impact that's hitting the lunar soil, the lunar regolith, and it's melting a bunch of, material in a localized area, and that is cooling down below the Curie temperature. So yeah, again, I think there's more uncertainty with the basalts, but even there have been studies looking at the calibration factors that we use for room temperature paleointensity methods. And we think that we're within a factor 2 or a factor 3 of the right answer. So even if we're getting very high fields early in lunar history, if we get 100 microtesla, even if we cut that down by a factor of about 3, we're still talking about a 30 microtesla magnetic field, which is similar to what we have on the Earth. But I mean, there's definitely more work that can be done in refining those estimates, but we don't, in terms of like planetary science accuracy, which is of course like much less awesome than earth science accuracy, it's still pretty good. Like we still do appear to see a difference in paleointensity that is not just related to the rock type. It's probably some kind of real signal.
Another one from the Discord is, can you use magnetic field observations to figure out crustal mineralogy or composition?
Well, maybe not so much looking at the natural remnant magnetization, because that can be affected by a few things, but we can definitely like heat samples in the lab to increasing temperatures and like in a known field, and kind of see at which point it doesn't record magnetization anymore, which tells us about the composition of the magnetic carriers. I wouldn't use magnetism to infer stuff about the mineralogy of the rest of the rock. I would just leave it to the magnetic stuff.
We have another one on the Discord that says, thanks for the talk. Could you touch on how the measurements from space magnetometry relates and compares to those paleomagnetic lunar rock samples?
Yeah, that's a great question. So the thing about when we measure lunar rock samples in the lab is we can actually get a paleointensity estimate for a rock. So we have like a better understanding of what the strength of the field was that initially magnetized a rock. When we're looking at stuff from spacecraft, we see an intensity of magnetic field that's observed at altitude, but we don't actually know the volume or the magnetic properties of the rocks that are actually carrying the magnetization. So we don't have any way of determining paleointensity from crustal magnetism unless you make assumptions about the original magnetic source body. You know, you can say, well, if this is a sill that's 1 kilometer thick and 100 kilometers across, then I can try to infer a magnetization strength for that body based on the field that it's emitting. But again, you have to make a lot of assumptions, which may or may not be even remotely accurate. So basically what I think, the crustal field studies are good for is getting an idea of whether a rock unit or an area of perhaps a certain age is magnetized or not by a dynamo. We also don't know, in the crustal mag, like how much iron or how many magnetic minerals are in a given region, what the concentration of that is. So again, it's good for saying like yay or nay on a field being present. And it's also good maybe for getting paleopole estimations, because you can invert for directions, whereas on the lunar samples we have from the Apollo missions, in the vast, vast majority of cases, we don't have any directional information, because these are just rocks that were lying on the surface. They had already been excavated by some impact. They do not retain their original direction in which that they cooled. And so if you want to have any directional information, that's where crustal mag is better than paleomag. However, I think that this may change in the next few years, because we wrote a white paper to NASA, basically giving them instructions on how the Artemis astronauts should collect samples moving forward. And we asked them to try to collect oriented samples that have been documented properly, so we can actually get oriented results like we do on Earth, but on the moon. So, I mean, it's possible that that situation will improve, and you can get robust results from paleomag, but until then, the crustal mag is the only way we can get directions that are reliable, and we don't even really know how reliable that is too.
We have time for just one more question. There's one that's come in the Zoom, and it says the moon was orbiting closer to Earth 4 billion years ago. Could that have had an effect?
Yeah, so that's a question. That's a good question. Basically, dipolar magnetic fields like the Earth's, they decay with distance as a function of like 1 over radius or distance away cubed. So it turns out that even if you back extrapolate the position of the moon to where it was closer to the Earth 4 billion years ago, the field strengths that you're getting are still on the order of like nanoteslas, tens of nanoteslas. So you're still not even there in terms of what you need to do to explain the paleomag signatures.
That's brilliant. Thank you. There is more on the Discord. So I direct you over that. There's a good discussion going on. So thank you very much for a really interesting talk.